Sí. Bueno, no es perfecto, pero en vez de apuntar al público, que tampoco aporta mucho. Estrado. Sí, estrado. No, ya está, ya está. O sea, no es perfecto, pero he cambiado la vista del estrado. Es que la alternativa es no verlo, porque lo está proyectando desde su ordenador.
Acá sí que se ve mejor, ¿no?
Sí, mejor, tienes razón. ¿Eh? Ya, y así que te parece, así se captura. Los demás eran un minuto. Más que nada para grabarlo y luego.
Please take your seat. We are about to start. Okay, so welcome. Welcome to the second day of the QTYR. Today, it is my honor to introduce Dr. Johannes Feist. He's a very distinguished researcher at the Department of Theoretical Condensed Matter Physics and the Condensed Matter Physics Center, IFMAC. They're at the Universidad Autónoma de Madrid. He has published more than 120 articles, according to Google Scholar. And he has received several prizes, such as the Young Scientist Prize by the International Union for Pure and Applied Physics. He finished his study of physics at the Vienna University of Technology in 2006, where he also obtained his PhD in 2009. And after that, he did 2 postdocs, one of them in Boston at the Harvard-Smithsonian Center for Astrophysics, and the other one here in Madrid at the Department of Theoretical Condensed Matter Physics, where he currently works as an associate professor. So today he will shed some light on the topic using cavities to modify material properties. So please, Johannes, the stage is yours.
Thank you for the introduction. I guess I should be close to the microphone. So I will talk basically, or let's say my talk will have 2 main parts. The first one will be about science, exactly on the topic of using cavities to modify material properties. It should take about an hour. And since this is a workshop for young researchers, and this is a tool that we have been developing for a few years now, that possibly may be useful to some of you, I thought I would spend like 15 minutes to tell you about this tool that we have developed for basically doing quantum algebra analytically and letting the computer do the commutators and so on for you and not having to do it yourself. But let's start with the science part. So as I said, this is the topic that we have been in some sense working on for close to 10 years, I would say, of using cavities to modify material properties in a very broad sense. And as a short outline of the scientific part, I will start with introducing the general idea, which is specifically based on this method or idea of strong light-matter coupling and the formation of polaritons, hybrid light-matter states. And then I will talk about 2 separate applications of these ideas. First, on trying to modify excited state properties, talking about several different topics that we have been working on, specifically also something that has been kind of taken over the group in some sense in the last few years, which is this method of mapping between really nanophotonic systems and quantum optics approaches. And then in the end, I will also talk a bit about how we can modify ground state properties or low energy properties of materials within cavities. So as a kind of general introduction of the ideas, here in Madrid, we come from kind of the field of nanophotonics, and there usually the idea is to tailor material properties to control the flow of light. And in some sense, what we've been doing in the last years is to kind of twist this around and say, can we actually use the light and the vacuum field specifically to modify material properties? So specifically, this means that what we want to do is use cavities that modify the electromagnetic environment, that modify the electromagnetic modes that are available, equivalent to saying I'm modifying the vacuum fluctuations. And this leads to effects such as strong coupling and polariton formation. And this really has kind of become a blooming field in the last few years, where people have really entered from very diverse fields, from nanophotonics, quantum optics, condensed matter physics, chemistry, etc. The basic idea is very simple. We all know lasers. They're made up of many coherent photons, and we know that this is a very good way to kind of manipulate matter. But alternatively, I can think of kind of making each photon strong by confining it in time and or in space, and then making the single photon interaction strong, which actually, so I think most people here is a very natural idea. In some sense, the physics that we're using is the same as you have in coupled pendula. where if I couple two pendula together, the new eigenmodes become either symmetric or antisymmetric oscillations, where that actually then have different frequencies. The antisymmetric one oscillates faster. And if I do this instead of with two pendulums, I do it with one photon and one meta excitation, charge oscillations typically, I get the same. I get new modes of the system, but now the antisymmetric and symmetric superposition turn out to be mixtures of light and matter, which we call polarity. Be a bit more precise, let's look at the simplest model possible, which is a single two-level emitter inside the photonic cavity. So this is the well-known Jaynes-Cummings model. And the coupling between the transition and the two-level emitter and the light field is given by this value G, which is in the dipole approximation nothing but the transition dipole of the two-level emitter times the field strength of the one photon inside the cavity. Equivalently also of the vacuum fluctuations. This is the same. And this field strength, this will become important many times during the talk, is inversely proportional to the square root of the volume within which this photon is confined. And if I do this, and I also take into account that my photons can leak out through the mirrors and the emitter can emit into free space and not into the cavity modes, which are decay rates described by these rates kappa and gamma. If I'm in the regime where the coupling strength G is much smaller than gamma and kappa, what I'm doing is the so-called Purcell effect, which is basically just modifying the radiative decay rate, and I get exponential decay of an excitation in the emitter, for example. Maybe faster if I'm coupled to the cavity, but it's fundamentally the same physics as in free space. But if I increase the coupling strength and I reach this so-called strong coupling regime, which is when G becomes comparable to the rates gamma and kappa, what I get is so-called vacuum Rabi oscillations, which means that if I start with an excited emitter, what it will do is emit the photon into the cavity mode, but since the coupling strength, which is basically tells me something about the rate of how fast this energy exchange is faster than the decay of the photon out of the cavity, what will happen is that the photon is reabsorbed by the same emitter. And this gives me oscillations in time, which are exactly the so-called vacuum Rabi oscillations. Vacuum because there's no external field driving the system. I just have a single photon that comes from the single emitter that I started with. And if I think of this in an eigenstate picture, what I have is really hybrid light matter states, so-called polaritons, which I write here, which are basically just superpositions of the excited emitter in state E, and the cavity, the one photon in the cavity, which we label as 1 here. And exactly this energy difference is the Rabi frequency with which the Rabi oscillations happen, because if I start with the emitter and the excited state, that's a superposition of upper polariton and lower polariton. So in the time dynamics, I will see exactly the oscillation with the relative energy difference between these two. Okay, then there's a third regime, the so-called ultra-strong coupling regime, which occurs when G becomes comparable to the frequencies of the emitter and or the cavity. And what I get in that case is that I not only modify here the excited states, I also modify the ground state. So basically I get a shift of the ground state energy, and my ground state also becomes in some sense a hybrid state, where I have in this simple model to lowest order in perturbation theory, the ground state with the emitter in the ground state and 0 photons in the cavity. Then I have a correction where the emitter is excited and there is a photon in the cavity. An important point to realize here is that this correction actually goes with the sum of the two frequencies. Here the frequencies don't show up at all because I assumed that the two frequencies are the same. Here this should basically be 2 omega 0, but I wrote it like this to make clear that even if omega C and omega E are different, this works equally. This doesn't depend on resonance. This will also become quite important later because it basically means that if I want to do these kinds of things, I really cannot just assume that I have a single mode. A single mode approximation, the same as the two-level approximation for emitters, works because I have some resonant physics that are more or less decoupled and detuned from other energies. In this case, there's really no tuning condition. I also want to mention that this physics of this ground state energy modifications is very closely related to Casimir-Polder physics. And the Casimir-Polder energy shift that you may have heard of an ultra-cold atom trapped in front of a surface or so, there it's actually important that I take this into account as well. Okay. Another interesting effect that happens and that we deal with in, let's say, probably 95% of cases is that when I don't have a single emitter, but I have many emitters, what I get is the so-called collective strong coupling regime. And it turns out that in that regime, the Rabi frequency that splits between my polaritons is enhanced by a square root of n factor that basically comes from the fact that the mode that my cavity interacts with now is a distributed excitation where the photon or the excitation is coherently distributed over all emitters. And if you remember that the single emitter Rabi splitting, which is the omega 1 here, was inversely proportional to the square root of the volume, this means that in the end, if I basically fill my mode volume with emitters, what I get is a square root of the number of emitters divided by the volume, which is nothing but their density. So what this tells me is that in the end, if I have this collective strong coupling regime, the Rabi splitting that I can achieve is basically only determined by my emitter properties, by their density and by their dipole moment. And what the cavity mode is doesn't really matter that much, which means we have a lot of freedom of choosing very different architectures. One important feature to take into account here and to have in mind is that I get these two polaritons, which are now coherent distribution of the excitation over all emitters, but I also get already in the single excitation subspace n-1 dark states in this simple model where I have just a single cavity mode. Because I have, of course, I have n emitters, which means I have n possible ways to distribute one excitation on the system, and those don't disappear. I only get two polaritons, which are the mixture of the coherent excitation with the cavity, and then all the others are basically orthogonal to the cavity and stay at the bare excitation of the energy of the emitter, and play actually an important role in many of the dynamics that we see in the experiment. Okay, as I mentioned, in the end, what matters is that I have a large density and a large dipole moment, and it turns out that organic molecules are actually really nice systems to reach this strong coupling regime. Because they have large dipole moments, they can be packed very densely, they can basically sit next to each other without disturbing each other too much. And that means that I can reach Rabi splittings on the order of 1 electron volt or even more, which is really a very significant fraction of the excitation energy, which is typically on the order of 2 or 3 EVs. Another advantage of the organic molecules is that they have a large exciton binding, meaning if I excite them, they stay excited. The electron and hole don't tend to split. Even at room temperature, they are stable, so I can do this at room temperature. And since the Rabi splittings are very large, it also means that it works with very bad cavities, because even if the decay rate is very fast, if my Rabi splitting is 1 electron volt, the decay rate can be 0.1 eV, and I still reach the strong coupling regime without any problems. So that means I can use resonators or cavities with a quality factor of 10, which is lifetimes of femtoseconds, and I still get Rabi splitting. And that means, in that sense, again, that anything goes, not in the philosophy of science way, but in the sense of saying I can do any photonic system, and I can basically reach strong coupling if I put enough molecules there. Typical systems where we do this are, for example, Fabry-Perot microcavities, so just two plane mirrors. And in that case, I have in-plane translation invariance. So what I usually look at is exactly as a function of in-plane momentum, the transmission spectrum, I think, in this case. And I see the energy of the photon mode, in that case, depends on the angle. And I see the dispersion of the bare photon, which is the yellow line, and the excitation energy of the emitters is basically independent. And after coupling them together, I get these two new curves, which are the lower polariton and the upper polariton. And I see they're really nicely split in this case by 0.3 eV or so. I can do the same actually with surface plasmon polaritons, which are bound photon modes that are bound to a metal surface, or in reality to any surface where the sign of the dielectric constant changes, and they basically exponentially decay into both the air or vacuum and into the material, and really guided along this surface. And if I now put molecules on top here, I again see as a function of in-plane momentum this Rabi splitting. And in the most extreme case, if I use these nanoparticle setups with localized surface plasmon resonances, where I can really confine photons to very much sub-wavelength volumes, so meaning here what I call a photon, well, we will discuss this later, but it is confined to something where the mode volume is on the order of tens of cubic nanometers. So many orders of magnitude below what in free space you would say is the maximum confinement, which is roughly lambda cubed. And in that case, I can even reach the single molecule strong coupling limit, shown here, where I get for a single molecule, well, if the dipole is aligned with the field, I get the Rabi splitting again with the lower and upper polariton. Okay, so after this introduction, as I mentioned, I will talk about two different kind of flavors of what we want to do with these kind of effects. One is to modify excited state properties, and there's really already many experiments and many things that have been shown to work and have kind of cool effects. And this is exactly dependent on this case of strong coupling, where the cavity mode is resonant with the excitations, and I get strong coupling and polaritons. And basically the idea there is, in most of the cases that I really want to use, that my polaritons are now neither material excitations nor just bare photons that do not interact, but they are hybrid light matter quasi-particles, which means that they interact with each other. It also means that, for example, in contrast to a bare exciton that just kind of sits on a molecule and maybe hops to the next one, if it's part photon, it's really a coherent state that is distributed and can propagate at almost the speed of light. And we can use these kinds of things, for example, to look at polariton transport. Exciton polariton condensation is a huge topic where people have shown exactly that since these polaritons interact with each other, but their effective mass is extremely low, they can do Bose-Einstein condensation at room temperature. It's been shown that you can modify photochemistry because you're modifying, in some sense, the states of the matter. And so we'll go into, I will show a bit more about this. And then the second part is this modifying of low energy properties, which up to now is mostly theory, where the idea is to modify, in some sense, properties that are not resonant with optical excitations, but modify things that happen at very low energies, for example, superconductivity, ferromagnetism, ferroelectricity, ground states of molecules, and so on. And as I mentioned, cavity modes in that case really don't need to be resonant. And this is very closely related, or basically the same effect that we talk about when we talk about ultra-strong coupling, and as I mentioned, to Casimir-Polder forces, or dispersion forces, as they're sometimes called more generally. Okay, so let's start with this first part. I just want to give kind of a brief overview of some applications that have been done with polaritons. Well, the first one is, in some sense, almost trivial, but it's an interesting thing to think about. What I can do is, if I put the molecules into a cavity and I really go into the strong coupling regime, I can completely modify, in some sense, where my molecules absorb light. So if I have some molecule that I want to use, for example, for a solar cell that has very nice properties, but it maybe doesn't have the absorption spectrum to absorb the photons of the sun most efficiently, one idea is I put it into a cavity and shift the absorption peak to a completely different energy. So in this case, you see I can really kind of something that used to absorb extremely broadly here. Once I have it in the cavity, it really absorbs at these two frequencies. In this case, this was an experiment that was done by Carl Börjesson that we collaborated on, where it was exactly this idea of using a molecule that stores solar energy, but that has a slightly too high absorption spectrum. And then it was just, we showed that we can push it down and still get this kind of energy storage. As I mentioned, another way that we can do is, or another effect that has been done and used for a long time, is that we can really get room temperature Bose-Einstein condensation or polariton lasing. So whether you call it Bose-Einstein condensation or polariton lasing depends in some sense on the details, on whether it's in equilibrium or not. So I don't really want to go into this. But the basic idea is that we use bosonic stimulation. We use the fact that these polaritons are effectively bosons, so they can all collapse into the same state. And if I pump them hard enough, so if I put enough polaritons into the system by just shining a strong laser, and it doesn't actually have to be that strong, I can reach the regime where they all collapse into a single state, and I see that all my polaritons are now at a single in-plane wave vector, in this case at the bottom of this dispersion band that you see here when it's more weakly pumped, and they're all at the same energy. And I see this kind of the same picture that we maybe have seen many times in ultra cold atom gases, where you get Bose-Einstein condensation. It basically looks the same here. And a very nice feature of the systems in this case is that since they're partially light and they're sitting in the cavity and leak out, the leakage conserves the in-plane momentum and the energy, so I can directly measure basically the quantum state or the condensed state of my system by just looking at it with the lens. I don't have to do what I have to do in ultra-cold atoms, where I have to make the cloud expand and then try to get the momentum distribution from that. I can just look at the system and I see it. So for the experimentalists, this is apparently quite nice. Another application is to use exactly what I mentioned before, that the colors are kind of off. Okay. That since polaritons are really delocalized states, I can make energy transport a lot more efficient than it is usually in a molecular system or in any disordered system of dipoles, where I have to, kind of, if I think about a system where I want to pump in energy from one side and get it out on the other side, if I'm not in a cavity, basically it would have to hop from dipole to dipole, and if there's disorder, this is very inefficient, and even without disorder, it's not super fast. And then the idea is that if I bring this into strong coupling and I have polaritons, I get states that are really delocalized over the whole area, and they don't care about the disorder anymore. The disorder just determines how much each of the dipoles contributes to the polariton state, but it doesn't really affect my transport anymore, because the transport in that case doesn't work by hopping from side to side, but works by from the outside directly coupling into a completely delocalized mode that is both here and here. And what we have shown then in this paper, almost 10 years ago by now, is that the transport efficiency can be increased as we turn on the Rabi splitting, so as we turn on the strong coupling, by something like 7 orders of magnitude for this very simple model. And this has been shown in experiments in, let's say, much more complicated setups than the simple model that we looked at. But for example, here it has been shown that in a material where outside the cavity the propagation length is maybe 10 nanometers or so, in the cavity you can get long-range polariton propagation over distances of tens of micrometers. So this is again really several orders of magnitude. So now let's go to kind of this part on reactivity and energy transport. And this is one of the important points that I have neglected up to now, is that molecules are really not two-level systems, right? So up to now we have painted this, but in reality a molecule, reality is always hard to define, but in other models that we theorists like to look at, the molecule looks like this, where I have really atoms shuffling around. I have water solvent flying around, doing bridges and disappearing again. So I really have a lot of things going on in addition to just a nice two-level system, especially at room temperature. And another way to see this is, for example, if I look at the absorption spectrum and the emission spectrum of the molecules, if this was a two-level system, that would be a single peak in the middle, and I would absorb and emit at the same frequency, just a transition frequency, right? In the molecule, I see I have a very broad distribution, exactly because of nuclear motion, and typically I absorb at higher frequencies, and then my molecule relaxes, the energy goes into vibrations, and I emit at lower frequencies. This is the so-called Stokes shift. Another way to look at this is the so-called Jablonski diagram, which is kind of here shows all the different kinds of states and processes that happen in molecules. So as you can see, it's a mess. But the basic takeaway is to say molecules have really many nuclear or vibrational degrees of freedom, and they typically have very large exciton-phonon coupling, meaning the state of the electron, the electronic excitation, really changes how my nuclear motion proceeds. If you have done molecular physics, basically what I'm saying is the potential energy surface of the molecules, which determines the nuclear motion, depends on the electronic state, and quite strongly. And that means what I usually get is really fast nuclear dynamics on timescales of femtoseconds, which, if you remember, are also roughly the timescales of the Rabi splitting and of the decay rates of the kind of bad cavities that we often use in this field. So everything happens roughly at the same timescales, and I have no good a priori reason to neglect any of these effects. This means this is both a challenge and an opportunity, because it means we can do things with it. If this was few orders of magnitude slower than anything else, we could neglect it, but we also couldn't use it. For example, one way where you can think about using it is to say, if I have molecules that can actually undergo chemical reactions, and it was shown a few years ago, well, quite a few years ago, that if I do this, if I put a molecule into a cavity that can undergo an isomerization reaction, meaning that when I excite it, basically one of the bonds here opens, I don't want to go into detail, it twists and two molecules move away from each other. And it turns out that if I do this inside the cavity, and in this case being on-resonant, this proceeds a lot slower than it does outside the cavity. They show that even if I'm in the cavity but I'm not resonant, nothing changes. And this was kind of one of our original motivations to go into this field. And what we realized is that one way to describe this is really by basically extending the simple picture that we had before from two-level systems to thinking about exactly the potential energy surfaces that describe the nuclear motion of molecules. So kind of in the simplest model again, if I say I have a molecule with just a single nuclear coordinate, the ground state in now is not just a single energy, but becomes an potential energy surface that depends on the position, and the same for the excited state. And for example, if I'm in the ground state, my nuclear wave packet would be sitting here, and then the transition energy would be roughly up to here. And if I put this now into the cavity, this would be the bare excited state of the molecule, but the ground state that it couples to with one photon added has the same nuclear behavior as the ground state, because I'm just adding a photon. Before I do any coupling, I'm not changing anything about the behavior as a function of nuclear position. So what I get is this other dashed line, and then these two couple together, and I get two new potential energy surfaces that don't look like any of the surfaces of the original molecule, but also are very much not just Rabi splitting of a two-level system. And that means that I can understand now chemistry going on this modified polaritonic potential energy surface, and we have shown that specifically if you also take into account again that we usually have many, many molecules, you can use this to quite efficiently suppress photochemical reactions. We have shown, for example, that you can photoprotect the uracil RNA base that usually can sometimes undergoes photo damage if it becomes excited, and by bringing it into strong coupling, we show that it can be suppressed. Another nice idea that we have been working on, or that we did a few years ago, that I liked, was that we can use the fact that our cavities exactly are usually very bad, meaning that they emit the photon very quickly, to do something like a pump probe experiment that I often want to do to understand dynamics without having to send in a second laser pulse. So basically the idea is to send in a single laser pulse. What will happen is that the nuclear wave packet starts moving on these surfaces, and if it emits very quickly, I can basically look at the time resolved emission and understand and learn about where was the nuclear wave packet, because its energy will depend on where it is in this oscillation. Another kind of relevant process that we have looked at already in quite a few different projects, for example, recently in this one that Maxime, who is sitting here, was involved with, is looking at energy transfer between polaritons. So now not energy transport in space, but looking at how can I transfer energy from one polariton state to the other. And it turns out that again, kind of this delocalization of the polaritons is very important. And in this case, the dark states, or sometimes called exciton reservoir, this is the ER here, become really what determines the dynamics, because it turns out that if I take into account these vibrations, my nice upper polariton tends to extremely quickly relax to the polaritons, because the vibrations basically shake it, and the coherence is lost, and it goes into this bare molecular excitation. But then if the lifetime there is long enough, it can actually decay, since kind of vibrations always tend to take away energy. In the end, the systems always want to go down if they have a relaxation channel. So although this is slow, in the end, they will usually end up in the lower polariton and then emit from there if the cavity lifetime is slow, again, relatively fast. And the fact that this rate is slow and this actually can be shown to be suppressed with the factor of 1 over n, has been called the large n problem in this topic because it actually suppresses a lot of the physics that would be very nice to have. And there's a lot of effects where we want to use polaritons to change dynamics, and if I get stuck in the exciton reservoir for a long time, I cannot do that because those are basically bare molecule excitations. And what we showed in this paper is that the theories that predict that this should go with 1 over n are actually true by basically designing different cavities with different lengths where everything stays the same apart from the number of molecules that are involved. And we showed that to a reasonable approximation, it really scales as 1 over the number of molecules. Another paper, which actually also involved Maxime, that we showed recently, and that is here an extension of these ideas to the case of where I have two different types of molecules, so what we call a donor and an acceptor molecule. In this case, the donor molecule is actually the same one that we just saw before that can undergo a chemical reaction. And the idea is to excite the donor and then use the polaritons basically through these types of processes to excite to get the energy into the acceptor molecules. And usually in bare molecular materials, this is a process that happens over nanometer scales. And again, because of the delocalized nature of the polaritons in the cavity, you can extend this to hundreds of nanometers, even micrometers. And what we showed in this case is that if in addition I make my donor molecule one that can undergo a chemical reaction, I can really turn on and turn off this polariton-enabled long-range energy transfer by controlling this photochemical reaction. Okay. Continuing on with this kind of idea of long-range energy transport, it has been shown exactly that if we now look at this long-range energy polariton propagation in a time-resolved manner, so here really saying I excite the system with the laser pulse at one spot and I look as a function of time how the polaritons propagate, and I look at this average position, or in this case the average mean squared distance from the starting spot, I can really identify as a function of the energy where I excite. This is experiments by Tal Schwarz and very similar ones by Milan Delors. First, ballistic transport that basically here scales linearly, and then kind of it stops. And in this case, I kind of see a clear switchover. In these ones, it's most easily seen from something that expands. In this case, it turns out to be quadratic in time to something that expands linearly in time, which is then characteristic for diffusive transport. And there was kind of a lot of discussion of how does this actually happen, because in principle polaritons, if I just think of them as nice systems with the polariton dispersion relation, should just propagate ballistically with the group velocity, which is just the derivative of the dispersion rate, which we learned in second year physics. And what we did is, in collaboration with Gerrit Grönhoff, who is in Jyväskylä in Finland, doing really molecular dynamics simulations inside the cavity where we calculate the nuclear motion of the dynamics in these semi-classical methods, and looked at this energy propagation. And what we find, if we plot again now the wave packet in time, in the theory we can really plot this with down to logarithmic probabilities, we find exactly this kind of two regimes of transport, mostly here in this case where we have losses included. And we realized that this switch over from ballistic, very fast transport, which is in some sense the nice one that we would like to use, to the diffusive one is really, again, because of the exciton reservoir, because of all of these dark states. So the polaritons get, even the lower polaritons here that usually we think about being kind of isolated from the reservoir, get reabsorbed into bare molecule states, which are basically static, and then they get emitted again and reabsorbed again, and only when they're in the polariton, they propagate. And this kind of cycling and propagation only in part of the wave function leads then in the end to this diffusive behavior. And if you include losses, interestingly, it also looks like your propagation actually goes backwards over some time. This is a kind of artifact just because of the fact that my kind of the fastest part of my wave packet is also the lossiest part, which because that's the polaritons that leak out of the cavity. So if I look at just the wave function that is left in the cavity, basically what happens is that the parts that have propagated the furthest disappear, and then it looks like my wave packet contracts again. So there's a lot of kind of, let's say, unexpected dynamics in these kind of systems. Okay, and now let's switch to kind of these sub-wavelength cavities, which is the idea of saying, instead of looking at distributed systems, we are going to use plasmonic and hybrid nanocavities that really provide this extremely strong sub-wavelength field confinement. So as I mentioned before, the mode volume associated with these cavities can really be like 7 orders of magnitude below what you can get in a normal optical cavity, which is on the order of lambda cubed. And that means that I get an extreme enhancement of light matter interactions. And it has been shown that you can reach single or few emitter strong coupling, again, still at room temperature with the organic molecules that are also extremely broad. And if I do this, of course, I avoid this large n problem, and I also maximize, in some sense, these local changes. So I maximize how much each of my molecules, or whatever emitters I use, in this case it was a quantum dot, is really modified and how much their quantum states change. For example, one very interesting application of this is in terms of quantum nonlinear optics, of saying, for example, here, what they set up, this is 2 experiments that run at roughly the same time by the group of Christoph Galland and Jeremy Baumberg, is to say, if I put now a molecule inside one of these extremely tiny nanocavities, and I set it up that my system also has an infrared resonance, can I upconvert infrared light through a Raman process that is enhanced extremely strongly because of the nanoscale confinement, because of these super small mode volumes? And can I do, in some sense, efficient infrared light detection or upconversion on, well, theoretically, let's say, going to the single photon level? I think in these experiments, they were at the level of 10 to the minus 5 efficiency or so. But there are good reasons to believe that this could be enhanced to close to, let's say, unit efficiency. So in order to be able to kind of treat these types of processes, the first question that we actually have to ask is, how do we understand the quantum light matter interactions in such systems? And then afterwards, how can we actually use this for ultra-fast quantum technologies? So the idea here is always to say, I know that I have this ultra-strong, ultra-small mode volume, so I can make everything very fast. But the price I pay is that I have very fast losses, because I need to use metals basically, and metals always have femtosecond lifetimes for the optical modes at best. So I need to be really fast, and then the question is, can I be still efficient? And in order to describe this, what we want, or what we actually need, is a quantum description of the light matter interaction in arbitrary structures. But the first question we have to ask then is, what do we actually mean with light and matter? So this is now very similar to the talk that Carlos gave yesterday. So if you were listening then, you can sleep for a few moments, but I will repeat it anyway, and also I have a bit more time, so I think it's not bad. The idea is that kind of, if we think about traditional quantum optics or cavity QED, we have these nice setups where we know that the cavity mode is just an electromagnetic field confined between mirrors here. And this confinement gives me discrete modes. And then I get some perturbations on top, which are basically the losses that I can leak out. But if I use good mirrors, that can be extremely small. But in our case, this is not at all the system that we are looking at. We are looking at this kind of nanophotonic systems where my so-called light mode is actually basically resonances of, for example, metal nanoantennas, where what I really have is electrons moving around, electrons sloshing around in the metal. And these are what actually give me this sub-wavelength field confinement. So these nanocavities, here we're talking about length scales of roughly 1 nanometer, really work because what confines the light is electron motions, or is electrons moving around in the material. And there's even some indications that you have effects due to the specific positions of single emitters, of single atoms within the metal, which is what people call pico cavities. And then what this means is that now my material structure, my antenna, that is what we want to use kind of as the cavity, are really themselves very much included, and their dynamics describe what are my light modes. And what we call the photons here, what we want to call the photons in our cavity QED-like setup, are really already themselves mixed light matter excitations. For example, surface plasmon polaritons that I mentioned before already. They're called polaritons because they are themselves coupled modes between electron oscillations in the metal and propagating photons. And this also means that the losses in the material and also radiation, which is usually very efficient and fast, are really now integral to the description. And I don't have just very nice sharp lines for my modes. I have lifetimes usually on the order of femtoseconds. And the method that we use, or the framework, is this so-called macroscopic quantum electrodynamics description, which was developed over several decades already, and not by us, just to be clear. We just use it. The general idea is that what we want to do is separate my system, for example, this idea, into the emitter, can be a molecule, can be a quantum dot or whatever, that I want to describe as a quantum system, basically a collection of charged particles, and then I can do quantum chemistry to know its structure. I can just assume it's a two-level system. That's what we do many times. And then the cavity, which is in some sense a completely arbitrary material structure, but we assume that it's big enough that it kind of only has linear response, meaning that I can describe it through macroscopic electromagnetism, basically Maxwell's equations that we have all seen. So if I assume local response, that basically means it's fully described by the permittivity and permeability as a function of position and frequency. And the general idea of macroscopic QED is, after I have done this separation, basically what I will do is take the cavity material that, as I just said, is described by linear response, and linear response means harmonic oscillators. So I can write down a quantum model that describes my macroscopic Maxwell equations just as a collection of coupled harmonic oscillators. I just have to find it. This was done by smart people. And a very important point, and conceptually, I think, very important step that needed to be done on this is to realize that dissipation, which usually is what people struggled with, saying that a dissipative system is hard to quantize. Dissipation can be essentially, again, just described by lossless harmonic oscillators that are a bath, that are coupled to my light modes, and that are just kind of internal excitations that I don't see. That's really kind of what happens in the material, right? Losses means that my energy goes into modes, oscillations of the atoms, of the electrons, or whatever, that are not coupled anymore to the outside. And if I realize that, it means that I can also just represent them by coupled harmonic oscillators, and in the end I get a huge system of infinitely many harmonic oscillators. But if I wrote it down smartly, I can basically show that the equations that these harmonic oscillators fulfill are exactly the macroscopic Maxwell equations. And we know how to solve them, and we just call the solution the Green's function. Right? This is what the Green's function is. It's the formal expression for the solution of the equations, in this case of the Maxwell equations. And since that fully describes the response of the, or let's say the behavior of the macroscopic Maxwell equations, it turns out that I can rewrite my whole system just in terms of these Green's functions. And then quantization actually turns out to be simple, because harmonic oscillators we know how to quantize. We just promote the canonical variables to operators, and we get a quantized medium-assistant electromagnetic field, which is again nothing else but a collection of bosonic modes, which are harmonic oscillators. So how does this look? Well, this is the general expression that Carlos also showed already yesterday. And this is really for any system. So here we don't assume anything. And that's also why it looks kind of not super nice to work with, let's say, because my field now, which is now really the medium-assisted field, turns out to be described by an infinite continuum of harmonic oscillators at every point in space, at every frequency, because I can have light at any frequency, with any polarization direction. So these are vectors that have three directions. And I can have, this is in some sense already an approximation. Here I'm just using electric dipole response of the matter and magnetic linear response of the matter. So I get type of excitation. This P can be either electric or magnetic excitations. And these are orthogonal operators, so formally the nice independent harmonic oscillator boson operators. And then kind of, this is completely general, always looks the same. This is where the details of the system matter, which is the expression for the electromagnetic mode, the electromagnetic field operator, and I can write down roughly the same or very similar expressions for the magnetic field or the vector potential or whatever observable I want. And what I get here is that it's basically fully determined by something that is the electromagnetic Green's function, this sub p, there's some prefactors that we don't need to really worry about. And basically what I see is that the electric field operator, due to each mode at position r prime, is determined by the Green's function going from position r prime to position r. So look, nice, formally really nice that we can do this, and impressive, I think. But in practice, I have this problem that it's really a 4D continuum of modes, 3 space and 1 frequency. I have 6 discrete degrees of freedom for the Cartesian directions and the 2 types of excitations. But I find, very importantly, that all the information is really encoded just in the dyadic Green's function. And again, this, in some sense, it's always easy to say in hindsight, but this should have been obvious from the beginning, because we know that the linear system is fully determined by its Green's function, right? So the question that we have been working on is, can we make this usable in some sense in the context of trying to do something like cavity QED, nonlinear quantum optics, and so on. This is, of course, has been very useful in many different contexts. For example, Casimir-Polder forces and so on. You do this, you do it perturbatively. This time you kind of integrate out all of these modes, and if you integrate them out, you get usable results. But for what we want to do is where we get strong coupling and so on, I want to do something more. And what we really have been doing and working on is trying to find a way to couple or to combine these traditional ideas of quantum optics, where I have discrete modes, often only a single one. I have Lindblad terms for my losses, with the way that we think in nanophotonics about our systems, where I have continuous modes for any frequency interaction, and really the Green's function or the Green's tensor is what determines the dynamics. And it turns out the concept that really connects these two worlds are resonances. And to be a bit more precise, basically what we can do is use a lot of things that have been developed in the theory of open quantum systems to do this connection. So let me be a bit more precise. If I now take my macroscopic QED system and I describe just a single emitter, it turns out that I can actually already, just from that, simplify from this 4D to a 1D description, because I can basically do a unitary transformation of all the electromagnetic modes to simplify the Hamiltonian, and at each frequency I only get a single mode that couples to the emitter, but it's still a continuum of modes, not discrete modes. And it turns out that what fully describes the interaction between the emitter and the electromagnetic modes is the so-called spectral density, this J of omega here, that is basically proportional to the local density of electromagnetic states at the position of the emitter. And it's given, again, by an expression that is the imaginary part of the Green's function. So it's directly related to the imaginary part of the Green's function. And also very much related to the Purcell factor that you may have heard, because the Purcell factor is nothing but the spectral density of my specific system divided by the spectral density of free space, the typical omega cubed scaling of spontaneous emission. And this spectral density is also the central quantity that in open quantum systems we always deal with. And as I said, it fully characterizes the cavity. And what this means is that two environments that have the same spectral density are really completely indistinguishable for the emitter. So an emitter only knows the spectral density, it doesn't know anything else about its environment. And then it turns out that this is exactly the idea that we can use to make simple models that look like the ones of quantum optics out of these complex spectral densities. So it turns out that if my spectral density is a Lorentzian, which is kind of a resonance peak as we are often used to, where I have a width kappa, I have a central frequency omega c, the peak position is exactly the chi squared over kappa that in cavity QED you may have seen from time to time. This spectral density is exactly equivalent to having a Lindblad master equation with just a single lossy mode. So if I can replace this Hamiltonian where I have a continuum of modes at all frequencies by a Hamiltonian where I just have exactly the Jaynes-Cummings model. I have my emitter, I have a single cavity mode, I have a coupling of that mode to the emitter through basically the dipole operator times A plus A dagger. And then I have a Lindblad term that describes the losses of my cavity mode with rate kappa. So this rate kappa is exactly the bandwidth here. And if I have multiple modes, I can just, that basically just gives me a sum of Lorentzians, or the other way around. If I have multiple Lorentzians, I can just write it as a sum of multiple lossy modes. So this is already very nice, and implicitly, maybe not too explicitly, but implicitly has been used for many years. And if I have nice isolated resonances that are really just Lorentzian, this is in some sense enough. But it turns out that this is not actually the case for the spectral densities of the systems that we are interested in. For example, if I look at something like this kind of plasmonic nanogap antenna with two spheres and an emitter in the middle, these are spectral densities as a function of different parameters. I see that I have some peaks that look kind of nicely Lorentzian, but I have this broad peak that is kind of asymmetric and so on. And especially if I go to this so-called hybrid systems, where I take a plasmonic nanoparticle, which has localized resonances and very large field enhancement, and I now put it into an optical cavity where I have standing waves, and I couple these two together, the spectral density that I get, which is this red line here, really doesn't look like a sum of Lorentzians at all anymore. I have here interference patterns. This is people usually call a Fano resonance-like structure. And here the same, where it's a plasmonic nanoantenna on top of a photonic crystal cavity. And again, I get a peak, like a double peak structure that is not just two Lorentzians. So can we now find an equivalent few mode model where I don't just use single independent modes, and I maybe can still describe these kinds of spectral densities? Well, it turns out that yes. And it's actually a very simple step that offers a huge amount of flexibility. It was actually surprising to us that this makes such a huge difference. The idea is to say, instead of having independent photonic modes, we're going to have coupled photonic modes, and each one of them decays independently. And it turns out that you can again show that this is actually exactly equivalent to a spectral density that is described by this simple expression. It's the imaginary part of the inverse of n by n matrix that just contains the energies and couplings of the modes and the losses in the imaginary parts. And if I have n modes in my model, this is an n by n matrix. And I just take its inverse, which is not hard to do, and I take the imaginary part, and I get this equivalent spectral density. And it turns out that these interactions, having basically non-zero values in the off-diagonal, give a huge amount of extra flexibility in getting different forms of the spectral density. So what we can do now is to say, for any nanophotonic system where we have calculated numerically with whatever Maxwell equation solver that we want to use, the spectral density, we can just fit this to a model of this form with n modes and get the parameters of my equivalent quantum optical system. And this is really importantly the only approximation we use in the method. So this fitting is the only step where there's any approximation. All the rest is in some sense exact. And for this test system, which is also the one that Carlos showed yesterday, we get, so this is a plasmonic nanoantenna embedded in a high dielectric microsphere. We get the spectral density that is, as we see, quite complex with lots of peaks and specifically with lots of interference structures in these peaks here. And it turns out with just 20 modes, which is basically the number of peaks here, I can really fit this essentially perfectly. Whereas if I use these non-interacting modes, the peaks I can still get quite nicely. So this would be the kind of old way to do it. But what I don't get at all is exactly these interference structures here or here. And also I get backgrounds that I really don't really want. And that can actually change the dynamics. So this means what we have is really now a direct mapping between nanophotonics and quantum optics. And in some sense, a surprising side result of this to us was that what we find is that the couplings and losses in some sense do not commute. What do I mean with this? If we go back here, we have a system of coupled harmonic oscillators, and each of them is lossy. So now you could say, okay, coupled harmonic oscillators, linear coupling, I can always diagonalize, right? I just get different harmonic oscillators. That's true. But if I do that here, these losses will not be diagonal anymore. They will be off diagonal. I will get this typical coupled or let's say, coupling terms in the losses. So in some sense, I'm stuck with either of these two not being diagonal. I cannot both make them diagonal at the same time. And one way to say, or to understand this, is to say that what this means is that my coherent and incoherent interactions do not commute with each other. And this is really the fundamental difference between having just a sum of Lorentzians, which is what I get if they interact, if I can write both of them diagonal, or if they don't. And it turns out that for a huge amount of photonic systems, you need these non-commuting losses. You need something that is not just a sum of Lorentzians, that is just independent modes. And so this, in some sense, implies that mode interactions are an intrinsic feature of nanophotonic systems. And this is really also a regime of quantum optics that has not been explored much, right? If we write down models, we usually write down uncoupled modes. And even if we take more than one, which already is kind of not that common, we usually don't assume them to be coupled. And as we see here, this can really lead to new kinds of interference structures and new kinds of properties. What I show here is just that it works, basically. So the black line is an exact solution of the dynamics of the emitter if I start excited in the previous system, and we see that with our model we lie exactly on top. If we use this non-interacting fit, it really fails quite dramatically. I just want to mention quickly, we don't need two-level systems. We're just fitting fully the photonic mode structure. So even if it's, for example, a four-level system, we get exactly the right, the correct dynamics. Again, the solid lines are the kind of a brute force solution, and the dashed white lines on top are with the model. And the very nice feature of this is that we also get directly access to the spatially resolved electromagnetic field. So for example, if I now say I put this emitter in here, and I excite it and I start my dynamics, what I see is really the photons propagating through the system and getting emitted. I get here now, so this kind of more or less Rabi oscillation where the emitter population goes down and then goes up again, and I see how this is reflected in my emission spectrum. And I want to mention this is really, I guess this already was clear, but just to make sure, this is not the same as you would get if you just do a classical simulation. Here you really need to do the quantum simulation. This is the intensity. The expectation value of the field for one photon field is always 0. As you saw yesterday, if you do if you say I don't want to actually do 20 modes, I can remove all of the ones that are not resonant with my emitter, and Carlos showed that nicely yesterday. And how do I actually, am I with time? Okay, so I'm already 1 hour. Yeah. Actually. Okay, then I'll just say we can extend it to multiple emitters, and it also works. That means I can look at energy transfer between different emitters now. And actually, this is what Diego and Maxime also have been working on over the last year. This is the talk by Maxime today, so I won't even go into any detail. But basically, this is showing that also these ideas can be used for doing ultra-strong coupling. And just to quickly mention this kind of this idea of that I might need coupled modes. For example, we have been able to show that by doing so, for exactly a kind of model system where I assume a plasmonic nanoparticle inside an optical cavity, we showed that we can use this to engineer a new type of nonlinear photon interaction, an effect that we call non-Hermitian photon blockade, where I basically get single photon emission, not because my energy levels are detuned in the system, but because I managed to basically do detuning in the complex plane, where I prevent the absorption of a second photon by making the second excited state in the system very lossy. Just going to mention this. If you're interested, I recommend you look at the paper. And I will, well, I think I can still a few minutes of this. This is really quite fast. So the second part that I wanted to mention is to this idea of modifying ground state properties, as I said, low energy properties in some sense. So for now, from now on, we will only think about kind of internal dynamics of the Hamiltonian that are at much lower frequencies than the relevant cavity frequencies. And then the question is, how does a cavity in that case affect the effective low energy Hamiltonian? For example, can it induce long range order or phase transitions or things like that? Here, importantly, we are not going to assume two-level systems or anything like that, but we will assume that all the internal energies that we're interested in are much smaller than the relevant photon energy. And it turns out what I can then do is exactly integrate out the photon mode. In this case, we're still now thinking of a single one. And there's many methods to do this that all basically give the same result. There's the Schrieffer-Wolff transformation. You can do path integrals. There's a Hep and Leap. You can also do perturbation theory if you're careful. And in the end, you get an effective Hamiltonian where I get my original one and then the dipole coupling between the emitters and basically the cavity mode at the position of, well, emitters or whatever excitations I'm looking at. And I get a factor that is 1 over omega c. But there's no resonance here. So as I mentioned, if this does not depend on resonance, what I really should do is include all the photon modes, not just take a single one. And again, we can do that very straightforwardly by using microscopic QED. And it turns out that even though I have this 4D integral with continua and sums and so on, Green's functions have a lot of very nice analytic properties, and I can do manipulations. I think I have to do like 3 different steps where I use different integrals. I need to use the Cauchy theorem and so on. But in the end, we get a very simple expression where the effective Hamiltonian is again just coupling an effective term where the dipoles are coupled through an effective coupling, lambda ij, that is again given by the Green's function, in this case evaluated at 0 frequency, because exactly I assumed that the energies that I'm thinking about are all very low, so are effectively 0. And this means that this is actually nothing but the electrostatic response of my material system, which is meaning the response at 0 frequency. So this is, in some sense, just the electrostatic interaction between dipoles in the presence of the cavity. Again, if we go back, this is something we could have expected, because I'm assuming explicitly that our energies are essentially negligible. So if I have no frequency, what I should get is the 0 frequency response, which is the electrostatic response. But what this also means is that any models that just use a single mode can give very misleading results, because if you use a single mode, you get very easily exactly collective behavior, collective couplings, because a single mode might couple equally to all emitters. So I get kind of all-to-all couplings between my emitters. If I do electrostatics, I just get electrostatics. It's very different. But it turns out you can still use it. We showed here, and maybe I will go very quickly, that for a model system where we assumed we have kind of ferromagnetic particles that each one have an internal phonon mode that is coupled to the electromagnetic field, this effective coupling can in this case actually induce an effective biquadratic spin-spin interaction. So you get an effective Hamiltonian, or you have spin squared here. And the interesting part about this is that usually in magnetism, the interactions are with spin itself and not with spin squared. And since this is the square, it means that this interaction does not distinguish between ferromagnetic and antiferromagnetic order, because it doesn't matter whether they are aligned and whether they point in the same direction or not. It just matters whether they are aligned or not. So this is kind of a new type of magnetic interaction that you can induce with this kind of processes. And it turns out in this case, the transition, as you cool down the system, you get a phase transition, but it's in this case a first order transition as opposed to a second order transition in conventional magnetism. Okay, and with that, I'm already finished with my part about science. I want to thank all the team and my collaborators. And I also want to mention we actually have open PhD positions inside a European international training network and postdoc positions on something completely different on attosecond quantum optics. So if anyone wants to do that, please contact me. This is in collaboration with Alicia Palacios. And with that, I guess we can do a 5-minute break. Then I talk a bit about this. So if you have any questions, of course, please.
So thanks for the talk. So when you make this mapping to this multimode stuff, you are at the end you are doing an approximation which is the Lindblad master equation. So you are dealing with systems with a lot of dissipation. Have you checked that this approximation is still valid?
That's a very important question. It's not an approximation. This is a very important point because we explicitly assume that our kind of bath is fully Markovian, which means that there's no approximation in writing it down as a Lindblad decay rate. So this is kind of the essence of the theory, that we are not treating the physical bath, we're treating a model bath that we impose. And if we make that completely frequency independent, it is 100% Markovian, and then the Lindblad term comes out like that exactly. That's not an approximation. The only approximation is in whether the spectral density that my model gives me is the correct one of the physical system. And that I can do with the fitting and making that fitting good enough. So this is a very important point here. There's no Markov approximation. It's not an approximation. So this is very uncommon, but it is the case here.
Essentially, you can. Yeah. So your map. These modes are coupled to a flat band.
Exactly.
A flat band. Okay.
Yes.
More questions?
Thank you. Just regarding the last part, when you study the ground state properties and so on. So you said you are integrating out the photonic modes. So, but you still have a Hamiltonian formalism. So it means that the two-level systems are in pure states, but they shouldn't. Is that right? Because you are integrating out.
No, this is just to get the effective Hamiltonian. They don't have to be two-level systems. They can be anything. The fact that we're at zero frequency basically means that there's no dissipation, because zero frequency, and if there's no dissipation due to that photon bath, because at zero frequency I have no photons. So normally you're absolutely right. I would get kind of the lamp shift kind terms that are with the real part of the Green's function and the decay-like terms that go with the imaginary part. But since we effectively end up at zero frequency, that one, the imaginary part is just zero. I don't have losses.
Okay.
Because I'm assuming that my frequencies kind of are low enough that they're essentially zero, which is kind of, well, there's no photon emission at 1 Hertz frequency or something.
Okay.
So that's basically the reason.
Okay, thanks.
Any more questions? We can take the small break.
I Ajá. ¿Cómo has venido tú? Sí,
So we continue with the talk.
Okay, so as I mentioned in the beginning, since this is a workshop for young researchers, I thought I will talk quickly about this tool that we have developed over the last years. Before going to it, just a very quick advertisement. If you're like me and you don't like manually converting between energies and frequencies and wavelengths and wave numbers and so on, or converting from dipole moments to decay rates and lifetimes and so on, I have this simple JavaScript tool on my webpage that you can use. You can also calculate kind of if you do an emitter cavity, you get a coupling strength, and these are kind of numbers that tell you whether you reach a strong coupling regime or not. This is the cooperativity. So I use this all the time because I'm too lazy to do real calculations. And this is in some sense also the motivation for this, which is kind of that we all know that computer algebra systems like Mathematica and so on are very useful, but they don't usually support quantum algebra, meaning non-commutative operators or objects. And I don't know if this can be read from the back, but it can actually be argued very strongly that non-commutative behavior is a very natural thing. I don't know if I want to read this, if you can read it. If not, I recommend SMBC comics. Just look it up there. But it's basically making the argument that non-commutative behavior is the least weird idea in history. If you go one step forward and then turn left, it's very different than if you go turn left and then take one step forward. So the idea of this tool is basically to remedy this, to say, let's see if we can make a computer algebra system, of course, much more limited than Mathematica. I don't want to get your hopes up too much, that supports quantum dynamics. Kind of the original motivation why a quantum algebra. Why we wanted to do this, or why we started doing this, is that we were treating an emitter coupled to a continuum of bosonic modes. So we had this Hamiltonian where this was a continuum, a single two-level emitter, coupling between all of them, and then external driving. And if you have many modes, this becomes very expensive to do. So this was before we did this few mode quantization, actually. And one way to do it is to look at operator expectation values in some kind of mean field approximation. And if you calculate them to first order, that's still nice. You just have to do commutations of your Hamiltonian with your operators, and you get the propagation equations for the different operators. And it's not too hard. But it turns out that here, for the first order operators, you get products of operators. So if I want to calculate the dynamics, I need to calculate the dynamics of the second order. It starts being a bit more annoying. I get here the third order showing up. So I need the third order. That starts being even more annoying, and I need the fourth order, and so on infinitely. At some point have to do a cutoff. And actually what we wanted to do here is to use a so-called cumulant expansion, where I say I don't treat the expectation values directly, but I consistently kind of expand it in terms of products of expectation values times the so-called correlator. And to second order, this is still reasonably nice. To third order, it's an expression that you can calculate. And if you go to higher orders, it again quickly becomes more and more annoying. And if you want to do the Heisenberg equation of motion, you realize that for this correlator, you actually have to get this equation of motion and this one, and you have to do all of this product. So the equation already just to second order kind of becomes very annoying. And then we said, well, actually, these equations really follow simple rules, but you have to do a lot of manual calculation to get it. And if you want to change the Hamiltonian, you have to do it all again. So the question becomes, who should do this? You, because I'm not going to do it, you know. So the other question is, maybe we can get the computer to do it. And that's what we decided to try. And this is what we basically implemented. So just a few very simple examples of how it works. And if you want to check it out, you can go to the, well, I'm not going to go all the way back. You can go to the webpage. I have relatively extensive documentation, and you can always write me. And for example, I can say I have a parameter omega that is a real parameter. This is what this PR means. And the A operators are already predefined as bosonic operators. So I can say I have a Hamiltonian that is a omega A dagger A, simple harmonic oscillator. And I want to calculate now the commutator of H with A. I get minus omega A. If I do it with A dagger, I get omega A dagger. If I do it with the number operator, I get 0 because the eigenstates of the harmonic oscillator. I can calculate not just the commutator itself. I already have a function to calculate the Heisenberg equation of motion. So here, without losses, this is basically the same apart from a prefactor of I. And for example, if I look at the change at the equation of motion for the population, I see that without losses, there's no change because it's again an eigenstate of the Hamiltonian. Of course, many times you want to add decay, so we can add Lindblad terms that are defined just by their rate and then the operator that does the decay. And if I now calculate the Heisenberg equations of motion, well, I get what I would expect and what I should get. But again, I don't have to do it myself. And if I add decay and pumping, so now I say I have a thermal bath and not just a single decay term, then the decay goes with the kappa times 1 plus the thermal population, and the pumping, so this is a decay with the decay operator, and the dagger operator has a pumping that is kappa times n. And it turns out actually the linear one doesn't change at all, but in the population equation, I get this pumping term with n kappa, and I can look at the steady state of this is obviously when A dagger A, the expectation value is exactly n. So there's thermal population as it should be. But I get all of this. So for example, what we saw yesterday, the levitated nanoparticle, we saw that the Lindblad term that they have actually doesn't go with the annihilation operator, but with the position operator. So I can quickly check if my Lindblad term is A dagger plus A, which is essentially X. I get exactly what Oriol pointed out, that I get linear increase of the population. And I don't have this term that is here with the decay. So I can also do, if I want to go a bit further, I can do a nonlinear oscillator easily. And I get the equations of motion. I get automatically these higher order terms. And as you see, you kind of can very quickly go to systems where doing all of this manually just kind of becomes maybe annoying, or at least it's kind of simpler if the computer does it for you. And actually, I also have this system where it automatically figures out the whole equation of motion, kind of a closed system of equations of motion. For example, in this case, where I tell it I want to use exactly this correlator expansion and drop all correlators to higher order than 2, and it automatically finds the operators that are inside my Hamiltonian and inside my decay rates and figures out kind of how many equations I need to get a closed system. I can do multiple modes, so we can do kind of a formal sum over indices. I can write this as a sum over I without specifying how many it is. So this is kind of just a formal analytic sum. and I get the correct equations of motion. I say for mode I have frequency omega I in the expectation value of A. In A dagger I Aj, I get exactly I omega I minus I omega j, and so on. And if I make the modes coupled, here this would be independent ones. If I couple them, I just give the omega 2 subscripts, I and j, and again I get the correct equations of motion, where here I now have a sum over all of these couplings. Instead of just one, where it's for mode I, this is omega I, and these pound symbols are kind of, since the sum indices have no real meaning, they just get replaced by pound 1, pound 2, etc. as sum indices. This is here. Instead of boson modes, I might want to have fermions, so I can do the same with fermions. And for example, I see that the equations for this system where it's coupled fermion modes instead of coupled boson modes are essentially the same, apart from exactly the one that is AI AJ. If you realize here you have two minuses. Here I have a plus and a minus because I have ordered them, and if I exchange fermions, I get a minus sign. So all of this is in there. I can define different names for boson modes. For example, this is this macro boson operators. So this is all written in Julia, by the way, which is this very nice programming language. And I can get the coupled system of equations for this system where I have a nonlinear coupling between mode A and B. If I feel inspired by the game yesterday and I say I want to have a boson mode that is a goal and I want to have a football as my parameter, I can do that as well. So this is just, you feel happy about the game yesterday as I did, and you see that the steady state here is 2 goals. Okay, you can also calculate vacuum expectation values, which is often useful for operator A. And in fact, by defining this operator S, you can say it's not just a vacuum, it's the system in state S, which is the same as the vacuum operation expectation value of this expression S dagger AS, if S is what generates my state sigma psi S. For example, I can say vacuum expectation value of A dagger A 0, of AA dagger is 1. The expectation value of A dagger A, if I have just a single creation operator that defines my state, is 1 because I have 1 photon, and so on. And I can, for example, make now superpositions and say, what is my expected number of excitations in mode N? If I say my state is excitation of mode M and mode N, it actually realizes that M and N could be the same, so you have a delta Mn here, and so on. And the real kind of, it's already kind of useful for these things, so I use it now many times, but one thing where it's really very nice is that I can do these big systems of equations of motion, for example here, where I say up to 3rd order. It generates 34 equations that are relatively long in fractions of a second. And if I, for example, do this where I do this correlator expansion again, up to 4th order in this case, I actually have 85 equations that by far don't fit on the screen. For example, this equation exactly has 61 terms that would keep going and going and going. And this does it for me. I don't have. And then you could say, okay, what can I do with the 60-term equation? That doesn't really help me. But usually in the end, what I want to do is implement it in code. And so we have a way basically to convert it to an expression that can be, that is basically the internal representation of code in Julia, and that can then be compiled to a function and can be used for numerical implementation. And that's basically already everything about this. And if you think it could be useful for you, I encourage you to check it out. And if you have any questions, of course, contact me. Thanks.
Thanks for the very nice talk, Johannes. Any question?
Why do you use Julia and not Python, for example?
Because it's compiled. So this is really optimized to get this down to the 0.01 seconds for equation systems of 85 equations. So that I mean, originally I used it because it has this very expressive type system. And then I expressed the commutators in terms of type relations, and then I realized this was horribly inefficient, and I rewrote it completely, and now it's basically because of the compilation. So I think in Python this would be way slower. I think for the kind of the simple system manipulations it wouldn't matter, but for these things where I really want to generate equations with thousands of terms, it really makes it huge difference.
And what is the idea? So you are defined like an object or something like this with some rules for the commutators.
The way that it works, yeah. There were at least 3 different implementations. Each one is different. So right now it's actually kind of converting to normal form is a bit more manual, which is not as nice algorithmically as the previous version, but it's much faster. So I do a merge sort where I look if I'm strengthening it. I don't want to really go to the code. I can show you and explain, but it gets a bit complicated.
Any more questions?
And another reason for Julia, just to mention, is that it has these very nice meta programming features, meaning I can generate code within Julia and directly evaluate it and get a function. So the original use where we used it, I actually wrote a function that automatically implements this whole equation system as a function that runs on the GPU to solve the differential equations. It's not in this package, but I have it. So I don't know how you would do that. I think.
Okay, so let's thank Johannes again. And now we can move to the coffee break.
Ah, vale.
You can leave your things here because the hall is going to be closed. So yeah.
Vale, mira, abre YouTube. Ahí está el link, y este no es el link que nosotros hemos puesto en Twitter, ni el que pusimos
pero
ayer.
ese link es genérico.
Claro, por eso, pero o sea,
Es genérico no de esta cuenta, creo yo.
a
Pero
ver, ábrelo en YouTube. O sea, es verdad que no pone nada, pero... O sea, ábrelo en Internet. Vale, tienes razón, vale. Pues no sé cómo lo hicimos el año pasado. A ver, abre YouTube. Yo creo que igual solo lo pausamos y ya está, y lo dejamos pausado y luego lo volvimos a despausar. ¿No?
Esto podemos cambiar la escena.
Nosotros a probarlo de Verónica. Ah, no está.
Podemos cambiar la escena. ¿Queréis ver?
Pues que no podemos probarlo de Verónica.
Podemos dejar esta escena.
Y esto es... No, deja poner background, hay un background.
¿Dónde?
A ver,
¿Dónde lo descargaste?
sí, está en el escritorio, pero el background es simplemente presentar la diapositiva.
Vale. Tío, podemos crear una escena que sea directamente...
¿El qué?
Podemos crear una escena.
Que sea directamente el Zoom.
Claro.
Sí, pero creo que ya lo tiene apañado el técnico, por eso digo que tiene que estar aquí, porque nos lo enseñó el otro día. Que lo tiene apañado para poner el Zoom.
Sí, él tiene cuenta A ver, ahí puedes darle a más en escena si podemos. Para que este tío no. Con todo el respeto a su labor profesional, pero no otro rocket science. No, simplemente más fácil.
Ah, para el background. Pensaba que te para Pero que, a ver, Álvaro, hay unos backgrounds creados que pone next thing.
Sí, pero...
Pues pon eso.
Pero si quieres dejar la emisión haciéndolo... ¿Tú qué dices? Poner...
Dejar la emisión, o sea, presentarlo como si fuera una presentación normal y
Vale.
dejar la emisión puesta. ¿No? Me parece lo más sencillo.
Vale, pero se van a ver las cámaras. Ah, vale. ¿De qué conecto?
Y esto lo movemos.
La fuente, ¿no?
O sea, quiero decir, eso es lo que hicimos el año pasado.
No,
Con eso.
sí,
¿Dónde lo
está
han
en el
metido?
escritorio. Background, sí, sí, sí.
Vale. Vamos a ver.
Venga, hacemos una pruebita de...
Sí.
Puedo volver ya.
Pues
Ábrela directamente. Vale. Dígame. Eh, sí, vale, de retransmisión.
claro.
Pero que
Sí, sí. Sí, pero porque se puede parar la red. O sea, aunque esto pare. Claro. Vale, lo que tenemos que hacer en
una...
eso tenía ya. Estaba bien.
Estaría bien que Verónica viera, por ejemplo, al público. Pero nosotros estamos compartiendo un vídeo, tenemos la cámara activada.
A ver. Te está saliendo por ahí, ¿no? Sí. Vale. O sea, si yo digo, tenemos a Verónica aquí que nos va a contar cosas.
Y algo, Álvaro.
A ver, Pollo, habla.
Hola, no os escucho, ¿eh? Ahora. Pero se escucha bastante, me estoy escuchando yo desde la puerta.
Hola Álvaro, te escuchamos genial. ¿Tú me escuchas si
Vale.
hablo por el micro?
Sí, perfecto.
Vale, genial.
Sale negro, que no sé lo que. Ya. Bueno, ahora está el vídeo. Sí. El link se
Claro, sí.
Ujú.
No.
order for it to sound. Like here it sounds, here it doesn't, here it does. Yeah, but then sort of, yeah. Well, I think this is a good place to stand. Anyways, yeah, ours are here. Dos, tres, cuatro, cinco. ¿Vale?
Abre el YouTube y preparamos esto.
Vale, ¿no? ¿Dónde tengo la grabación de aquí?
Es-
YouTube si lo pareces de un ordenador mejor.
Aquí, esto. Aquí. Vamos en ello.
Tú sabes pararlo a lo... Si lo oculto un rato,
También.
no. Y tú has subido la charla. Si no lo paro de aquí.